Hello, this is Ms. DB, and this is the last section of Chapter 1, and it's a very important one, and we will be using the ideas from this lesson over and over for the rest of the year. And it's on Intro to Parent Functions. So we are going to identify parent functions from graphs and equations and use them to model real-world data and make estimates for unknown values. So a parent function is just when you have a set of characteristics about a graph or an equation, then we can classify them into certain families of functions. The parent function is the simplest one of those that has those characteristics. Functions in the same family are transformations of their parent function. So the first one that you learned about was the linear function. There is constant too, but that's just a horizontal or a vertical line. But the linear function that we learned was y equals mx plus b. The most basic one of those is f of x equals x, or y equals x. The domain, this kind of funky looking r, means r is the real numbers. The domain is the real numbers, all of them. And the range is also the real numbers. It intersects at 0, 0. It goes right through the origin. The next one that you've learned about a little bit, and we're going to talk a lot about this year, is the quadratic, and that is f of x equals x squared. The domain of that is also the real numbers. You can let x be anything, but the y, the range, is going to be limited. In the parent function, the range would be that the y values are always going to be positive, so you can write that y is greater than or equal to 0. It also goes through at 0, 0. A cubic function is when you have f of x equals x cubed, and you can see that this one has some kind of twist and turns in it, like a fun slide. The domain is the real numbers, so x can be anything, and the range of this one is also the real numbers. Y can be anything. It also goes through at 0, 0. And finally, we have the square root function where we start at 0, 0, and then we kind of increase quickly and then level off, and it gets almost horizontal if you continue it farther on. The domain of this is that all of your x values are going to be positive. X is greater than or equal to 0. All of your y values for the range are also going to be greater than or equal to 0. It also goes through at 0, 0. Here's another way to look at the parent functions. I took constant off of there because that one's not very interesting. We have the linear, the quadratic, the cubic, and the square root function here. We also see that I've written out some characteristics of each of those. So some things about this family, this linear, all have in common. All linear functions are straight lines. The line may not be in the exact same position on a coordinate plane, but it's still a straight line. If the line slants the other way, then we know the slope is negative. So this one has a positive slope. If it were to go the other way, it would be a negative slope. The quadratic family looks like a U or an upside down U. They always have a vertex where the graph turns. So in this one, the vertex is right there at 0, 0. If the U is upside down, then we know the x squared term is negative. The cubic function turns twice. So it's, if you're moving up, it's got this little bump here, and then it turns and it starts going up again. The ends will always point in opposite directions. Right now it's positive. If it was decreasing from left to right, then it would be negative x cubed term. And finally, the square root function, they have an endpoint. None of these other ones have endpoints. All of these continue in both directions. This one only continues in one direction. They increase or decrease from that endpoint rather quickly, and then they level off to almost a horizontal line. If they decrease, there is a negative in front of the square root. So if this would have dipped down and then levels off, then that would have been a negative square root of x squared. All right, if you're using a graphing calculator like a TI-84 or something, sometimes your graphs don't look symmetric. They look kind of stretched out. So you might have to go to Z standard or Z square. In Sketchpad, we can go to graph grid form and turn it into a square that way. All right, so here's an example. We have a function here. We want to know what is its parent function. Is it linear, quadratic, cubic, or square root? So the best way to do this is to graph this in Sketchpad or on your calculator and then see what it looks like. Okay, so we can see that there's no exponent. So this one, if you graph this one, you're just going to get a straight line. So it's linear. So the parent function is linear and it's f of x equals x. So what you're supposed to do is say, how has it been transformed? It has been transformed from f of x equals x by translating down 3 units. It has moved down 3 units. So here they say it's a vertical translation of the linear parent function 3 units down. Sometimes that's easier to tell than others. All right, so here we have g of x equals x squared plus 5. We see it has a power of 2, so we're thinking it's quadratic. The quadratic function, hey, they forgot the squared sign on there, is f of x equals x squared. And the parent function you could graph on the same calculator or your Sketchpad, and you can graph better than me. It looks like a U shape where the vertex is at 0, 0. So we can see that this has moved up 5 units. So this is a translation vertically. It's moved up 5 units. Here's some from your worksheet. Okay, here's just a graph. It doesn't even have an equation. It says, how is it like the parent quadratic function? So here's a picture of the parent quadratic function. You have those on your worksheet so you can look back. And you're supposed to say, how are they the same? They're quite the same, right? Very similar. Except for if you look at where the vertices are. This one's at -1, 0. And this one's, whoops, I clicked a button accidentally. This one's at 0, 0. So the vertex of the transformed one has changed. So how has it changed? Let's see. Is the only thing that's changed is that all of these points moved over to the left 1 unit. So your transformation is going to be a translation 1 unit left. Or you can say it's a horizontal translation too if you want, by -1. So you still have to answer how are they alike and how are they different. Domain. The domain of this function. Is there anything that we can't let x be? Generally, the parent function, this one down here, has a domain of all real numbers, and that's what this would be as well. So you can try to make the fancy R if you want, or you can just say all real numbers. And the range? The range is not all real numbers. The range is, it will never be, the y values will never be negative. Both of these are pointing upwards. It's never going to get lower than y is greater than or equal to 0. Or you can write that all positive values of y, if you want to write it out in words. So all the y coordinates will be positive. Okay, for number 3, you're going to answer, how is this like the square root function? Here's the square root function parent function, and you can see that it's changed. Not a whole lot. 1, 2, 3, 4. In the parent function, at 4, it's at 2. At 1, it's at 1. In ours that has been transformed, we're at 1, -1, and 4, -2 for our points. So you can say how it's the same, how it's different. You can say what the transformation is. Might want to say the word reflection in there. And then say what the domain and range is. Now in this one for your domain, x is always going to be positive again. There's no negative x values. We don't use any of the negative x values here. So you can say that x is always going to be greater than or equal to 0. The range, however, the y coordinates are always less than or equal to 0 in this one, aren't they? In the parent function, they're greater than 0, but in this one, they're going to be less than 0. All right, let's see. Number 6, we have a graph, and this time they give us the equation of the graph. It's g of x equals -x squared. So you're supposed to say, what is the parent function? Is it linear? Is it quadratic? Is it cubic or is it a square root function? If you're going to abbreviate square root, don't abbreviate it as square. You've got to write the word root. So it is, you probably figured out, quadratic, and the parent function would be f of x equals x squared. Quadratic wins. The transformation is, let me just try to sketch. Here's your parent function. It's supposed to be right above that. So how has it changed? Has there been a reflection? Has there been a translation? Has there been a stretch? Has there been something we haven't talked about? It's either a reflection or translation. You can probably tell that it's a reflection about the x-axis. Now this one, you again have to pick if it's linear, quadratic, cubic, or square root, and then say how has it been transformed. This one's a little bit harder to do because here's 0, 0 way up here. It's barely on the thing. But if you look back at the parent function, the one that matches this that I just graphed, you can see that it has perhaps moved from here to about here, 1 point. So that can help you determine how has it been transformed. All right, sometimes we're just given a set of data points. We don't have a graph, we don't have an equation. All we have is a list of points. And then we are wanting to find an equation that's close to this that will fit these points best. And you'll be doing that a lot this year. If we can figure out what parent function fits this best, then we can adapt that. We can work with that equation with transformations in order to really get it to fit this data well. So here's a list of points. The first thing to do is to graph those points. And once we have a graph, we can start to connect those points and see whether it's linear, quadratic, cubic, square root, or some other function that we haven't talked about yet. So it looks like it's quadratic. It's not the exact same as the parent function, but it resembles the y equals x squared, the f of x equals x squared. And then you can even study a little bit more, especially if you, on top of this, were to graph the parent function. Let me get that on here, which goes through 0, 0, 1, 1, and negative 1, 1. And then it goes through 2, 4, and negative 2, 4. So these blue dots are the parent functions, dots, coordinates. So you can see that this has been stretched vertically, and they figured out that it was stretched by a factor of 3. It was all of the y coordinates were multiplied by 3. So it seems to represent a vertical stretch by a factor of 3. Now, they say seems to because we only have 5 points here. Maybe it does something different in the outer reaches of this graph. But from what we can tell so far, it looks like a vertical stretch by a factor of 3 of the quadratic parent function. Here's a couple that you're going to do. And you do not have to turn in your graph for this. You can graph these in Sketchpad or if you have a graphing calculator. I'm going to graph these in Sketchpad, and then I'm going to see if after I graph them, if I can tell what is the parent function, what was the transformation, what's the domain, and what's the range. So I have Sketchpad open and ready to go. All right, here are the problem for number 8. So to graph these in Sketchpad, we're going to go to plot points, and x is -3. I'm just going to put these points in, and then we have -1, -5. So this is good practice using Sketchpad, and a practical reason of why I make you use Sketchpad. It's a really nice graphing calculator so that you don't have to go buy a $100 one. If you already have a graphing calculator, you are welcome to use that if you are familiar with using that already. Okay, so I've got all of my points on here. And it looks like those points are all in the same line. So I'm going to go ahead and get my line tool over here. And I'm going to see if I connect this point with this one, Yeah, they're all going through that same line is going through all the points. So now I know that this is a linear function. Linear, which is f of x equals x. The transformation, let me graph y equals x, f of x equals x. All you would have to do is put the part after the equal sign. So f of x equals x is just, you just have to type x in. That's the parent function right there. I'm going to turn it green. So the green line is the parent function. It's hard to look at this without saying it looks like it's tilted. So the transformation there we go. Transformation. I'm going to write the equation of my new line. The blue one there. Okay, the slope is up 5 and over 1, right? Yeah, so the slope is 5, so y equals mx plus, and it goes through the y-axis at 0. So my new line, that helps me see the transformation. The transformation is a stretch, vertical stretch, I guess I should write, by a factor of 5. Because the slope changed. It was stretched up. And you can kind of see that it was stretched up along the y-axis. The domain, all real numbers. The range, all real numbers. Linear equations, unless there's a real world situation that's limiting them in some way, they're going to just be all real numbers. All right, and then the second one, I'm going to plot these points, -3, -1, and then that automatically put my grid system on for me. -1, -1/27. Let's see if I can do that in here. It's very close to 0, but not quite. Then we have 0, 0. I bet this is going to be cubic. See how it's kind of getting almost flat in the middle there? And then 3, 1. And then it's going to go up. Done. So you can, it's hard to see this one, and it's going to be really hard for me to draw this one with this marker tool, but it looks to me, it does not look vertical. It does not look quadratic. It looks to me like it's kind of going like this. Let me graph the parent function of y equals x cubed, or f of x equals x cubed. See how that also does that? But this one is flattened out. It's like compressed horizontally against the x-axis. Let me see if I can make my the one that I hand drew there look like that. What if I multiplied by a number like 4? This is just kind of an experiment. Nope, that made it kind of long. What if I change this? You can click and change it. What if I change it to like 0.4? It's not really. How about if I change it to 0.04? See, that's really close. So it looks like, and I was just guessing at what it was, but that line, this new one, that's very close to the way my other one was, isn't it? It's probably really supposed to be 0.03 or something. And you're not even required to find the equation. I'm just curious and wanted to kind of get it to match as well as I could. The 0.04 was actually closer. So it has been compressed. The transformation has been compressed, or is it stretched horizontally or compressed vertically? I'd say compressed vertically by a factor of 1 over something. Maybe it's 1 over 27. I'm going to put 1 divided by 27 in parentheses, so that I'm going to be multiplying my cubic parent function of x cubed by 1/27. Oh, look at that. That's what it was. So it's being multiplied by 1/27. So that's how that's the transformation. Whoops, a compression by a factor of 27, or 1/27. The domain is all real numbers. The range, all real numbers. It doesn't have a limit on it. All right, well, I think that was everything. We talked about that. Oh, this is just showing that we looked at these. If you just have 2 points, 0, 0, and 0, 1, that's not enough to find out what the parent function is, because look at those 2 points are on all 4 of these parent functions. So that's not enough. You need, the more data you have, the more accurate you are going to be when trying to find its actual function, its actual equation. And then there's an application problem where you would graph this real world data, and you could use that to estimate some future, in this case, when will these sales reach 10 million? So here's our millions along the side. At 5, it was at 12.6, so 10 million is right about here. You can see that the parent function looks like a part of y equals x squared, and you could estimate that that's going to happen at about 4.5 years. Okay, thanks very much, and have a great rest of your day.